And we'll start with question 1. This is strictly physics, okay? We have a circuit, an LCR circuit, which has 1 microhenry inductance. Let's write that down. 1 microfarad capacitance. And it has 1 kilo ohm resistance. They are connected in series to some voltage source. And we have these annoying questions where we have to check each and every option. Alright, we have to check. At omega almost equal to 0, the current flowing through the circuit becomes nearly 0. Is it true or false? Well, let's check. We know that the impedance is equal to the square root of R square plus XL minus XC the whole square. When omega is almost 0, XL is almost infinity. Not XL, sorry, XC is almost infinity. So yes, Z goes to infinity. That makes current go to 0. So option 1 makes sense. So A is the correct option. Then we have the frequency at which the current will be in phase with the voltage is independent of R. The frequency at which the current will be in phase with the voltage. So we're talking about the resonant frequency, right? Because that's the only frequency at which the current and the voltage will be in phase. And the resonant frequency is given by omega naught equals 1 divided by omega naught, right? 1 by LC, and is independent of R. Makes perfect sense. So B is perfectly valid solution. Then we have C. The current will be in phase with the voltage if omega equals 10 to the power 4. So again, they're asking for resonant frequency. Let's check. Resonant frequency has to be 1 divided by square root of, you have a micro here, 10 to the minus 6, and you have a C, that's 10 to the minus 6 again. That should be 10 to the plus 6. So omega should be 10 to the plus 6 for resonance. So nope, that's not the correct answer. So this is wrong. And lastly, we have at omega much bigger than 10 to the power 6, the circuit behaves like a capacitor. What does that mean? Well, we just have to check which one dominates. If omega is much bigger than 10 to the power 6, 10 to the power 6 is that resonant frequency, alright? So if omega is much bigger than 10 to the power 6, then XL is much bigger than XC. Do you see that? Because XL equals XC at omega equals omega naught, and XL increases with omega, but XC decreases with omega. So the circuit behaves more inductive, not capacitive. So the current will lag behind the voltage, and so it's inductive. So the answer C, D1 is also wrong, and therefore we have our first solution. Question 1 has A and B as the answer. Ta-da! Alright, let's quickly go to question number 2. Let's move down to question 2. We have for an isosceles prism of angle A and refractive index mu, it is found that the angle of deviation equals, minimum deviation equals A. So we have an isosceles prism. This is A, and these are equal angles. And we have been given that the minimum deviation D is exactly equal to A. Okay? Which of the following options are correct? For the angle of incidence I1 equals A, the ray inside the prism is parallel to the base of the prism. So here is the ray of light, and we want the ray of light to be parallel to the base of the prism. And that only happens when we are at minimum deviation. So I need to calculate the angle of incidence for which minimum deviation happens. So how do you do that calculation? Well, remember that at minimum deviation, I1, that is the angle of incidence over here, is exactly equal to the angle of emergence over there. It's exactly equal to this angle. the angle of emergence, and that is equal to some value I. From this, can we calculate what the required angle of incidence is? Yes, we must be able to do that. How do we do that? Well, you remember the formula mu equals sine of a plus d divided by 2 divided by sine of a divided by 2. This over here, my dear friends, is the angle of incidence for minimum deviation, and this is the angle of refraction for minimum deviation. And so the angle of incidence for minimum deviation turns out to be a plus d, but the d is same as a, so you add them, divide by 2, that just gives you a. And the angle of refraction for minimum deviation turns out to be a by 2. So option 1 is absolutely right. So a is correct, because at the angle of incidence for the minimum deviation is a, right? So that makes perfect sense. The second question is, at the minimum deviation, the incident angle I1 and the refracting angle R1 at the first refracting surface is related by R1 equals I1 by 2. Yes, look, R minimum is I minimum by 2. So that's perfectly right. So B is a valid answer. 2 for 2. Okay. For the third one, we have the emergent ray at the second surface will be tangential to the surface when the angle of incidence at the first surface is... okay. So what we want this time is this. We have our prism. So here is our prism. Alright, so we need to find out what is this angle over here for that to happen. That is not this angle, okay? That is not I min, because we are not getting minimum deviation. We want this to be 90. This is mu, so this has to be the critical angle C, and this has to be some angle of refraction R, and this is A. So from this we can understand that if you apply a Snell's law at this point, I get mu times sine C equals 1. Okay, because it's 1 times sine 90. That's equation 1. And I also know that R plus C equals A. So R is A minus C, which is just A minus C is a sine inverse of 1 over mu. Okay, now let's use at this surface the laws of refraction, and we will get 1 times sine I equals mu times sine of this angle. But sine of this angle is, we have to do sine A, you're taking sine of this, okay? So I'm using sine of A minus B formula. So it is, so this, think of this as B. So sine A cos B. What is cos of this? Well, let's draw a triangle to figure this out. If this is some angle B, then this is 1, this is mu, this is root of 1 minus mu square. So sine A times root of 1 minus mu square plus cos A sine B. So you get cos A times sine B, sine of sine inverse. So it's just 1 over mu. Okay, so this is what I get. And that has to be equal to sine A times mu times root of 1 minus mu square plus cos A. But I think we don't have mu, so I have to get rid of mu. The way I can get rid of mu is I can use the formula mu equals sine A divided by sine A by 2. This is 2 times cos A by 2. Alright, so that gives us sine A times cos A by 2. I get a 2 here. To 1 minus mu square, that's cos square. Is it 1 minus? It's mu square minus 1. I'm so sorry. Yeah, that's what I'm wondering. What is that? So it's mu square. So cos square, 4 cos square a by 2 minus 1 plus cos A. So I should get this. So let's see whether that is the answer. Sine A times okay. Oh, there's a mu down here. Oh, this is clumsy. There isn't this guy. This guy doesn't exist. I think that's right. Yep. Oh no, there's a factor of 2 missing? No, there's no 2 here. Okay, yeah. Alright. This makes perfect sense. Minus 1 plus cos A minus cos A. Minus. Oh my god. This is embarrassing. Okay. Alright, so yes. Third one is also an option. So C is also an option over here. Oh gosh. For this prism, the refractive index mu of the angle related by... No, that is wrong. Because we got mu as 2 cos A by 2 and it's a... Wait, I have to calculate what angle of prism, right? So let's do that. Angle of prism becomes mu by 2. And I have to do a cos inverse. And I have to do 2 times. Okay, yeah. Alright, so this one is not true. So A, B, and C. I think whoever did this missed one of the answers. Poor guy. Alright, so that is question number 2. Let's jump to question number 3. We have something. A circular insulated copper wire loop is twisted to form 2 loops of area and at the point of crossing, the wire remains electrically neutral. Okay, I mean insulated. Okay, they are insulated from each other. The entire loop is alright, the whole thing starts rotating. Okay, fairly simple problem, I think. Alright, before even we begin, there's one small thing you need to understand. When this thing turns, the EMFs will be in the opposite direction, right? So I hope you get that. This is very important. I think that's what the question is. Let's see in a moment. We have something like this. So when it turns, if the EMF over here is clockwise, the EMF over here is also clockwise, but notice, because if it's clockwise, it's trying to push the current this way, but over here it tries to push the current that way. And therefore, even before what the question is, I'll tell you the net EMF has to be equal to, if this is loop 1 and this is loop 2, it has to be equal to the difference in the EMFs. Okay, alright, so let's consider. The EMF induced in the loop is proportional to the sum of the areas. Oh no. Okay, that's exactly what A is wrong. It has to be the difference, not the sum. EMF induced is not the sum. That's wrong. Good boy. Okay, next. The rate of change of flux is maximum when the plane of the loops is perpendicular to the plane of the paper. I think that's a pretty standard solution. That's right. And the reason it's right is this. Look, right now the flux is maximum. Okay. But the EMF induced is proportional to d phi over dt. D by dt of B dot A. Okay, so that is proportional to, we can get rid of B and A because they are constants. So you get d over dt of whatever is the angle between them right now. It's proportional to, right now the angle between them right now theta is 0 degrees. Alright, and when you do this, we get BA. Okay, let's see, you have a dot, you have a cos there at some angle, you get a sine over here, omega t, and when theta is 0, EMF is 0. Can you see that? This is a pretty standard form problem, so B is right. The net EMF induced to both the loops is proportional to cos. No, it's not. It's proportional to sine. So that's not our answer. The amplitude of the maximum net EMF induced to the both loops is equal to the amplitude of the maximum EMF induced in the smaller loop alone. The net EMF is, you have to subtract these two, but 2A minus A gives you A, and so the answer has to be the same as A. Yes, sir. So D is the correct answer. Yes. Okay, let's go to question number 4. A flat plate is moving normal to its plane through a gas under the action of a constant force F. The gas is kept at a very low pressure. I think the low pressure stands for ideal gas. So, that's what you should do. The moment you look at the problem, try to analyze it. The speed of the plate V is much less than the average speed U of the gas molecules. That's going to be useful in approximations, I hope. Which of the following options either are true? At later time, external force F balances the resistive force. So we have to figure out the resistive force in this example. So here's the question. This is a good one. I think this combines your concepts of collisions and kinetic theory of gas. Alright, so here is a plate that's moving with the speed v, and you have molecules that are moving on an average with the speed u. So some molecules are going to go and come and bang over here, and some molecules are going to go and come from bang over here. And this is going to produce some force from the front. So there's going to be a net force on this side. That, let me call it as force F1. And then there will be a net force on this side, and there will be F2. And clearly, since this thing is going and banging into this, the force F1 is going to be larger. So the net force is going to be F1 minus F2. So that force has to be in this direction. Obviously, it's a resistive force. All right, so we need to find out the properties of this resistive force. Basically, I figure out what does it depend on. So it's a case of collision. So what we'll do is we'll change reference frame. We'll go to the plate reference frame. If you go into the plate reference frame, then the plate is at rest. And we need to add, we need to use relative velocities. And if you use relative velocities, then it's clearly, over here you'll have u plus v, and over here you will have u minus v. I hope that makes sense. Because if this is going into it, then this speed will increase, and this speed will decrease. And so after collision, this will have a speed of u plus v, and this again after collision will have a speed of u minus v. Again, this is from that reference frame. I can stick to the plate reference frame, no problem, because the force must be the same from either reference frame I calculate. So let's calculate the force from this reference frame. The incoming force, okay? Let's calculate F1. That force is the rate of change of momentum. So let's calculate the total change in momentum first. The change in momentum of due to one guy will be just mass of one guy multiplied by 2 times the change. Change in velocity is 2 times this, right? So 2 times u plus v. That is delta p due to one guy. Okay? But how many guys are there? I'm going to assume that the number of particles per unit volume is n. And so if I wait for exactly 1 second, I will see that I could go to a distance of, this is how I like to do these problems. I always wait for 1 second. And you will see that if there's a molecule over here, and then the minimum distance, or sorry, the maximum distance that we can go, or we can expect the molecules to come and collide in that 1 second would be if the distance is u plus v. Do you get that? All the molecules which are within this distance. So if I were to consider a box, a 3-dimensional box, and in that box, a box which has a length of u plus v, then all the molecules within that particular box will hit this guy in 1 second. And for that reason, I can now say that the change in momentum in 1 second, the total change in momentum in 1 second, delta p in 1 second, has to be equal to all the number of molecules that come and hit him. And the number of molecules that go and hit him will be n times, n is per meter cube, so n times the volume of that box, that's going to be the area A, this is the area A, times the length, u plus, you understand this? This is the total number of particles present. N is the number of particles per meter cube, and this is the volume, and so this is the total number of particles. But I know that each particle gives me this much, so I have to multiply this to get the total change in momentum in 1 second, but that is the net force. Change in momentum in 1 second, Newton's second law. Alright, so the net force over here is going to be proportional. I don't think, do I need to know the exact value? No, I think, because it's proportionality. Alright, so it's proportional to, we can get rid of this a, n, and m, and 2. It's proportional to u plus v the whole square. And I think by the same argument, yeah, pretty much the same argument over here, this will be proportional to u minus v the whole square. And the proportionality constant will be exactly the same. So the net force will be proportional to the difference of u plus v the whole square minus u minus v the whole square, which will be proportional to 4uv or uv. Okay, so this is the net force. Alright, so the question is, at a later time the external force F balances the resistive force. Yes, if you keep pushing and if the speed keeps on increasing, the resistive force keeps on increasing, and at a particular point it'll balance out. And so yes, A is definitely a solution. The plate will continue to move with the constant non-zero x. No. The resistive force experienced by the plate is proportional to V. That's exactly what we found out. C is right. And lastly, the pressure difference between the leading and the trailing faces of the plate is proportional to UV. Well, pressure difference is proportional to the force difference, right? Because if you want to get pressure difference, you just have to divide by A. And divide by A, you get the same answer. UV. Alright, so D is also a correct answer. Alright, so these are the 4 correct answers. 3 correct answers. Let's quickly move on to yay, mechanics. A block of mass M has a circular cut with a frictionless surface as shown. The block rests on a horizontal blah 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 blah. Okay. Please read it along with me. Pause the video if you want to. Alright, so here's the situation. We have this frictionless floor and the mass drops down and the radius over here is R. This radius is R. And this distance is also R. And basically we need to figure out certain properties. We need to figure out what V is, I think. The velocity of the point mass. We have to calculate the velocity of this mass. We have to calculate the position of the mass, and we have to also calculate the position of the point mass is. Okay, we need to calculate the position of the point mass. Position of the point mass at what value? At the instant. Okay, so we have to calculate the position of the point mass. And we have to also calculate the x component of the displacement of the center of the mass of the block M. Actually, B and C are supposed to be the same. Alright, let's calculate them. To calculate V, what we can use energy conservation. We can do the following. We can say, look, when it comes from here to here, it has energy, it loses potential energy mgh, which is same as mgr, and that becomes the kinetic energy of both the objects, alright? So it becomes half m v1 squared. V1 is the velocity of this guy. This is V1, which I'm gonna call, which is called as V, plus half m v2 squared. That's equation number 1. And we also know the conservation of momentum, so this is v2. We also know that m times v1 plus capital M times v2 should be equal to 0. So I could substitute for v2 as mv1, the negative sign, divided by capital M, substitute over there, and see what we get. So you get mgr equals half m v1 squared plus minus half, no, you get a plus because we have a squared, capital M times m squared v1 squared divided by small m squared. Is it? What is it? I can't make out myself what I've written. This is capital M, alright. So this is capital M squared. This guy goes, and we can lose m's over here, and that gives us v1 as, let's see, 2 goes over there, you get 2gr. You remove 1 plus m divided by capital M, you put a root over that. Alright, that's the velocity of the block. Yup, A is the answer. So A is an answer. The x component of the displacement. Okay, that's the next thing. Displacement is what I want. To calculate displacement, I'm going to use the fact that the center of mass displacement must be 0. That should be the same as the displacement of the first mass plus, sorry, it's not m1, it's m times displacement of first mass plus capital M times displacement of the second mass. Okay, that gives you, what is the displacement of mass 1? Well, it got displaced towards the right with r, it got displaced towards the left with x, but I usually like to call x as a variable, right? So I'm just going to call this as r plus x. I'm going to say, like, I'm dumb, I have no idea whether it's towards the right or towards the left. Plus, this thing got displaced by x, and that has to be equal to 0. So x has to be equal to, we have to get minus mr divided by m plus capital M. Yep, true. So B is a solution. The position of the point mass is x equals minus 2. The point mass must also be at the same position. Now, come on. The x position, right? I'm talking about. The x position has to be at the same. I have no idea what that stupid question is. Stupid option. That's not true. The velocity of the block. Okay, that's what I was thinking. Yeah, that's very easy. We have used conservation, right? We just substitute over here. The velocity of the block is minus m divided by capital M times v1. That is going to be square root of 2gr divided by capital M plus small m into capital M here. Does that look anything like what is given here? Nope, I don't think so. It doesn't. Nope. No, you can't reduce that to that form. No. So yeah, that's it. A and B must be the solution. Okay, moving on. Question 6. And we'll do that in the next episode. Stay tuned for more.